September 91, a 5.36 gram sample of NH4Cl was added to 25.0 mils of 1.00 molar NaOH, and the resulting solution was diluted to 0.100 liters. Then we have letter A. What is the pH of this buffer solution? Okay, so we got a lot of numbers here, right? They told us we have a mass, 5.36 grams of NH4Cl. We have a volume with the corresponding molarity of NaOH. Then the whole solution was brought to 0.1 liters, but the overall question is asking for the pH of a buffer solution. When we're talking about buffers, especially if they're asking for pH, the easiest way to do these types of problems is to just use the formula that was meant to answer a pH for buffers. That's the Henderson-Hasselbach Equation, which is this one right here. So first, let's just put this, over here for now. Now, Henderson-Hasselbach is specifically for buffer solutions, and look, it's already set for us to answer it in terms of pH, right? pH equals, and that's what part A is asking for. So now we just need to find out three things: the pKa of the solution, and then we have this base and acid system over here. Now just know that if we want to find the molarity of the base divided by the acid, this has to be the buffer system. Can't be any strong acids or strong bases. Keep in mind that, remember, when they talk about buffers, they have to be conjugates of each other, right? And remember, conjugates are always one hydrogen away from each other. So they look very, very, very similar. So if I just look at these at face value, NaOH with NH4Cl, those are not conjugates. So I can't just put these values into this equation. We have to find the conjugates. So let's just see what's going on here. Now the first thing is that I noticed that so maybe I'll just put A over here. So the first thing that I notice is that we're talking about NH4Cl. Okay. And NaOH. Now we just said that these aren't conjugates, so I just have to figure out a little bit more of what's going on. But I do notice that I'm dealing with NaOH, and from this whole chapter, NaOH is a very strong base, right? It's one of your 6 strong bases. So I have a strong base here. I'll just put Sb. Now, whenever you're reacting strong bases with any other, and I don't want to give it away, but basically remember that if you're having a base, bases can only react with acids, right? No two bases react with one another, and no two acids react with one another. So if this is a strong base, this has to be an acid, but we'll see exactly why that is. But if you have this idea, what we're going to do is we're basically going to make a battlefield. I think it's the easiest way to do these types of buffer titration questions. Instead of writing balanced equations and doing all that jazz, I just like to use a battlefield. And what do I mean by a battlefield? It's basically just a 3-tiered chart. So what I'm going to do is I'm just going to put a line here. And I'm going to have 3 things, just like that. And let's just make these a little straighter. That's good enough. So here's my lovely little battlefield. And how it works is that there's going to be 3 different components here. Now, there's only one thing that really, is set in stone. That the strong acid or the strong base has to be in the middle. Just works the easiest this way. So since we already identified that the NaOH is the strong base, I'm going to put that in the middle. Okay, and we know that this is a strong base, so maybe I'll just put Sb, strong base. Okay, so now I just have to figure out, well, what's the compartment that we're going to be using in terms of NH4Cl? Keep in mind that NH4Cl is a salt because it's an ionic compound. It can be broken down. NH4 is a polyatomic, and Cl is just a regular ion. So this breaks down into NH4 plus and Cl minus. Which one has the acidic property? Remember, bases only react with acids, so which one out of these two is going to be the acid? it's going to be the NH4 plus. I see that I have a positive up here, right? So that has to be an acidic component, and this has hydrogens. So checks out. So I'm only going to care about the NH4 plus. And since this is now a weak base, this is one component of your buffer. So this is the acid component of the buffer. So maybe I'll just put like buffer acid. Maybe I'll just put buffer A for acid. Now, did it really matter that I put the acid on the left or the right side? Absolutely not. You get to pick. Doesn't matter. I just put it on the left side. But on the right side now, I have to put the buffer base. And they didn't say what it was in this question because you have to figure that one out. When these two react with each other, you're going to form the buffer base. But remember, a base is only one hydrogen less than the acid. So since there was 4 hydrogens here, you just drop it down to 3. So the buffer base would be NH3. Okay, we're getting there. Now here comes the battlefield. These 3 are going to basically be interacting with each other to overpower the strong base or the strong acid that's in the middle. But if you're using this, just know that only moles are allowed, because moles are the quantity that can be additive or, basically subtracting from one another. So the next step that we have to do, we have the setup, but we have to make sure that all of our starting amounts are in moles. So let's go for it. The first thing I'm going to do is I have to change that 5.36 grams of NH4Cl into moles of NH4 plus. So let's do that first. So I'm going to say 5.36 grams of NH4Cl. Well, how do I go from grams to moles? Well, that's all the way back in the beginning, right? It's just that conversion. Grams of NH4Cl on the bottom. We got moles of NH4Cl up on top. And just keep in mind that I have to include the chlorine because that's what the compound stated. It was a gram sample of the whole compound, so I have to get the molar mass for the whole compound. And remember, if we're using the periodic table, it's always 1 mole equals whatever that mass is on the periodic table. So calcul's out, periodic table's out. Let's find what the molar mass of NH4Cl is. So 14.01 plus 4 times 1.008 if we want to be specific. And then we got 1 chlorine, 35.45. So I get 53.492. Grams cancel out with grams. Let's find out those moles. 5.36 divided by 53.492. Not the full answer here, so I'm going to give it a couple of decimals. So 1.002 moles of the NH4Cl. But now, how do I get moles of just the NH4 plus, right? Well, this is where our mole ratios come into play, but you could just kind of visualize it. Do you see out of this whole compound, how many NH4s are in this whole compound? In one whole compound, there's only one NH4, right? There was no parentheses saying that there was 2 of them, or 3 of them, or 4 of them. So it's a 1-to-1 ratio. For every 1 whole mole of NH4Cl, there's only 1 mole of NH4. So the number would be the same. Don't you love it when it's a 1-to-1 ratio? So this is now just the moles of NH4 plus. And that's the number that now goes on the top here. Okay. 1 out of 3 completed. Let me just make this a little bit better. Now, let's work on finding the beginning moles of the NaOH. Well, that came from 25 mils of a 1 molarity NaOH. Now, in this case, I'm not going to do a gram to mole conversion because they gave me a volume and they gave me a molarity. But if I remember my molarity formula, molarity equals moles divided by liters, I can find out the moles by just cross-multiplying moles times liters, right? So I can just say that, maybe if I just get rid of all this, the amount of moles would be equal to molarity times liter. Well, the moles of NaOH would be the molarity. They did tell us that we had a starting molarity of 1.00, and that has to be multiplied by the liters, but they gave me 25 mils. I have to first convert those 25 mils into liters, but that's easy. Milliliters to liters, you just divide by 1,000. Or you can move the decimal over 3 times to the left. So this would be 0.025, and if we want to keep the 0 over there, that's fine as well. So that's the liters, 0.025, and 1 times that's going to be the same number. So we're starting off with 0.0250 moles of the strong base. Okay, now we're left with the base over here. Did they say that we started off with any NH3? I'm searching, and I don't see anything about starting with any ammonia, which is NH3. So if we don't start with any of it, we got to assume that it's 0. All right, now comes the fun part. Here's where the battlefield comes to play. The whole idea about buffers is that if you add strong acids or strong bases, the buffer will gobble it up, and basically it won't hurt the system. Generally, the strong base should be the lowest number out of the two that you have. You will always subtract by the lowest number, and in this case, it is the buffer. It is the strong base. So, we're going to subtract by 0.0250. And as you can see, once we do that, there's not going to be any more strong base in the system. But this number gets to, what's going to happen with the acid or the base. Whatever number that you put as the smallest amount, that's going to trickle down into the acid and the base buffer system. So this has to be 0.0250, and this also has to be 0.0250. So I'm just going to put a line here, but now we just have to figure out, are these going to be additive or subtractive to each other? And are these going to be additive or subtractive to each other? Well, they're two different colors. You have an acid reacting with a base. They don't like each other, so they're going to try to destroy one another. And whoever wins is the higher amount. So in this case, the acid is going to try to take away. So it's going to be subtraction because they're two different species, an acid versus a base. On the other side, since I wrote them both in blue, base with base, that's additive. So anytime that you see two of the same colors when you're doing the battlefield, that's additive. Anytime that you see that you have two of different colors, that's subtractive. And I'm not talking about the strong acid or the strong base. I'm only talking about the battlefield between the acid and the base on the outside. So this would be plus. Now, let's just add these numbers in. So 0 plus the 0.025 is obviously that number. And now for the acid component, we're going to still have a little bit of acid left over. 0.1002 minus 0.025. I get 0.0752. And no more strong base. So we don't even care about this. But the thing now is that here is your final values for what happened after you added the base. And these numbers are the numbers that go into the Henderson-Hasselbach equation. There's only 2 units that are allowed in Henderson-Hasselbach, molarity or moles. So we don't even have to worry about the new dilution. That's just like an extra step, but honestly, the math, you could do it from the mole value. So that's what I'm going to do. I'm going to say that, okay, the base was 0.0250, and the acid, the remaining, was 0.0752. Okay, so we figured out this part. Now we just have to find out the pKa of the system, and from there, then we can get the pH. So pause the video if you need to, because I'm just going to get rid of this part on the left-hand side here. So bye-bye. And then maybe I'll just erase some of this. Beautiful. Okay. So now, pKa. Well, since this question was taken from a textbook, they are going to assume that you can go into the reference tables and find the necessary Ka values or Kb values that are needed for this problem, right? And that's what I did. I went to the back of the book and I found out that I did find a Kb value for the base, which is NH3. But the question is asking for the Ka, specifically the pKa. So the first thing I have to do is I have to convert the Kb value into a Ka value. But that's okay, because we know this formula right here. Kw equals Ka times Kb. If I want to solve for the Ka, all I would have to do to both sides is just divide by the Kb. Right? That cancels that out. So let's just do that. So I'm just going to say, okay, we're going to divide by the Kb. This now goes on this side. And now we have this little formula here. The Kb was what we found in the back of the textbook. So 1.8 times 10 to the negative fifth. And the Kw is also a standard number that probably you would have to memorize this one. If it's at room temp, Kw is 1.0 times 10 to the negative 14th. So let's figure it out. 1.0 times 10 to the negative 14th divided by the 1.8 times 10 to the negative 5th. This equals the Ka. And then we'll get the Ka value down here. So calculus out again. 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. I get 5.56. That's good enough. Times 10 to the negative 10th. Now we're almost there. We need the pKa. What's the formula between pKa and Ka? That's this formula over here. pKa equals the negative log of the Ka. Probably all these formulas you might have to remember, because chances are these are not going to be like on a cheat sheet. But could be. I hope that it is, because then it would be easier. But some teachers or professors, they're a little bit more strict. Okay. So now, the Ka value we just found was 5.56 times 10 to the negative 10th. So we could just plug that in and find the pKa. pKa equals negative log of 5.56 times 10 to the negative 10th. And the pKa would be equal to negative log 5.56 times 10 to the negative 10th. And I can extend this out a little bit. 9.2549. Maybe 255 we'll say, I guess. 9.255. That's good enough. And that's this number right over here. Okay. So now all we have to do is just plug in the numbers and solve. So I'm just going to get rid of this lower thing down here. Goodbye. And now I'm going to get ready. pH equals the pKa, which we just found out, 9.255, plus the log of the base number after the titration, after the battlefield. So that was, once again, it was this number here, right? 0.0250 divided by the acid number. That's the number that's left. There you go. Now you could plug this number in at once into the calculator. You could also just find the log and then add it to 9.255. I'm just going to do it into the calculator and get the answer. And that would be for letter A. So in this case, let's see, log of 0.025 divided by 0.0752. Okay, and then we're going to add that to 9.255. And let's see, 3 sig figs all around. So with pH values, technically that's the total after the decimal. So it'd be 8 point lucky sevens. 777. Yeah, that's it. Just checking for rounding. But that's the pH. So it's 8.777. Now, for part B, which I'll just do at the bottom, this one's pretty easy. Is the solution acidic or basic, right? Well, this just comes from what we know about the pH value. Just know that the dividing number is 7. Anything below 7 is acidic, so I'll just put A. Anything above 7 is basic, and 7 is the neutral value. So in this case, since we're a little bit above 7, right, we're 8.77, this solution would have to be basic. And that's the answer for B. I wish they were all that quick, right? Crazy. So we did A and B. I believe that there is one more number, part C, that's coming up in the next question. So if you guys are on the playlist, which I highly recommend you being, it's just easier to navigate through all the questions. I'll see you in a few. But if you wouldn't mind, please hit that subscribe button. Just helps the channel out. Thank you so much, and I'll see you in a little bit. Bye-bye.